3 times larger. I break the current, you see it 3 times larger. And this is the idea behind transformers. You can get any EMF in that wire that you want to by having many, many loops. You can get it up to thousands of volts. And that's not so intuitive. So Faraday's law is very non-intuitive. Kirchhoff's rule was very intuitive. Kirchhoff said when you go around a circuit, the closed loop integral of E dot dl is always 0. Not true if you have a changing magnetic flux. If you have a changing magnetic flux, the electric fields inside the conducting wires now become non-conservative. Kirchhoff's rule only holds as long as the electric fields are conservative. If an electric field is conservative and you go from point 1 to point 2, the integral E dot dl is independent of the path. That's the potential difference between 2 points. That's uniquely defined. That's no longer the case. If you go around once with this experiment, you get a certain EMF. You go 3 times around, you get a different value. Your path is now different. And that's very non-intuitive, because you're dealing with non-conservative fields, for which we have very little feeling. Now, I'm going to blow your mind. I'm going to make you see something that you won't believe. And so try to follow step by step, leading up to this unbelievable and very non-intuitive result. I have here a battery, and the battery has an EMF of 1 volt. Here is a resistor, R1, which is 100 ohms. And here is a resistor, R2, which is 900 ohms. And I'm asking you, what is the current that is flowing around? And you will laugh at me. You will say, that's almost an insult. I wish you'd given that problem at the first exam. Because E equals the current that is going to run divided by R1 plus R2.
Oh my goodness, what did I do? I forgot Ohm's law. E equals IR, remember? Not I over R. So R1 plus R2 should go upstairs. And everything that follows is correct, so you don't have to worry about that. This was just a big slip of the pen.
And so the current I is 10 to the minus 3 amperes. 1 milliampere. Big deal. Easy. Current is going to flow like this. Fine. Let's call this point D, and we call this point A. And I asked you, what is the potential difference between D and A? You will be equally insulted. VD minus VA. You apply Ohm's law. You say that's this current times R2. Absolutely. I times R2. So that is plus 0.9 volts. Now I say to you, well, suppose you had gone this way, then you would have said, well, I find the same thing, of course. Kirchhoff's rule. So indeed, if you go VD minus VA, and you go this way, then notice this battery, this point is 1 volt above this point. But you have in the resistor here, you have a voltage drop, according to Ohm's law. And the current times 100 ohms gives you a 1/10 voltage drop here. So VD minus VA is the 1 volt from the battery minus I times R1, and that is plus 0.9 volts. What a waste of time that we did it twice and we found the same result. So I connect here a voltmeter. The voltmeter is connected to point D and to point A. And I ask you, what are you going to see? The answer is plus 0.9 volts. And you will, provided that the plus side of the voltmeter is connected here and the minus side of the voltmeter there. Voltmeters are polarity sensitive. This is fine. Kirchhoff rule works. The closed loop integral from E dot dl going from d back to d is 0. So far, so good. Now, hold on to your chairs. I'm going to take the battery out. Who needs the battery? I'm going to replace the battery by a solenoid, which you see right here. And this solenoid, when I switch it on, is creating an increasing magnetic field. Only here. And let's assume that that increasing magnetic field is coming out of the board and that it is increasing. Lenz's law will immediately tell you in what direction the current is. If this magnetic field is increasing towards you, the current will be in this direction. The magnetic flux change, d phi dt, at a particular moment in time, happens to be 1 volt. An amazing coincidence, isn't it? E induced at the moment in time is 1 volt. So now, I ask you, what is the current? Well, you'll be surprised that I even have the courage to ask you that, because Ohm's law holds. The induced EMF is 1 volt, and R1 plus R2 is still 1000 ohms, so 10 to the minus 3 amperes. I really make a nuisance of myself when I say, what is VD minus VA? And you get annoyed at me and you say, look, the current I through R2, Ohm's law, V equals IR plus 0.9 volts. And then I say, but now suppose we go the other side. And we want to know now what VD minus VA is. And now, it's not so simple, because there's no battery. And so now, when I go from D to A, I don't have this 1. And therefore, I now find minus 0.1 volts. I find a totally different answer. I attach a voltmeter here. That voltmeter will show me plus 0.9 volts. Now I attach a voltmeter here. The same one. I flip it over. It's connected between point D and point A. It will read minus 0.1 volts. This voltmeter, which is connected between D and A, reads plus 0.9. This voltmeter, which is connected to D and A, reads minus 0.1. The two values are different. And I placed on the web a lecture supplement which goes through the derivation step by step, which will convince you that indeed this is what is happening. Why we can't digest this so easily is we don't know how to handle non-conservative fields. If you have a non-conservative field, then if you go from A to D of E dot dl, or from D to A for that matter, it doesn't matter, the answer depends on the path. It's no longer independent of the path. And so, if here is D and here is A, and you go this way, you find 0.9 volts plus. If you go this way, you find minus 0.1 volts. Faraday has no problem with that. Kirchhoff has a problem with that. But who cares about Kirchhoff? Faraday is the law that matters. Because Faraday's law always holds. Because if d phi dt is 0,